Hello everybody, welcome to episode 2 of AlgorithmsThread. I'm your host David Harmeyer. Today I'm going to be talking about RMQs, some things you can do with them, and how you can improve them from what people usually write, from building in order n log n to building in just linear time, and also keeping your queries in order 1. So the first thing that might be helpful to talk about is what sort of problems does an RMQ solve? So suppose you're given an array of integers, and maybe your array is like size 10 to the 5th or 10 to the 6th or something, and you want to answer a bunch of queries. So each query is like, in this range of integers, what is the minimum? So suppose your array of integers is like maybe 3, 1, 7, 2, 4, 3, 3, I guess. And then maybe you want to answer in this range, the minimum would be 1, in this range the minimum would be 3, and in the entire array, the minimum would be 1. So you have to answer a bunch of queries. Maybe you have to answer like 10 to the 6th queries, and you want to do each of them relatively fast. An RMQ can help you solve this problem, and it can answer each query in order 1 time. So segment trees can also solve this problem. They would do it in log time per query, but you can use an RMQ, and you can do it in order 1. RMQs are also kind of a little bit easier to understand than segment trees. I guess they're similar in difficulty. But RMQs are very helpful. So how exactly would you build an RMQ to solve this problem? Well, you have n different positions in the array, and I'll draw them each as circles. And I guess let's add an 8th number here. So maybe this number is a 1. That way we have a power of 2 in length. You don't need a power of 2 in length, but it's helpful for demonstration purposes. So what we're going to do is we initially store all of these numbers in the array in case we have to answer any queries of size 1. So that's just something we have to store initially. We'll also store the min across all pairs of numbers. So for each or all adjacent pairs. So for every 2 numbers that are next to each other, we're going to store what is the minimum of these 2 numbers. So the minimum of these would be 1. It's 3 and 1, so the answer would be 1. Then the minimum of these would be 1 as well. The minimum of these would be 2, 2, then this would be 4 and 3, so it'd be 3. This would be 3 as well, and this would be 3 as well. These aren't necessarily increasing, they just happen to be in this example. So then after we do this for all pairs, for all groups of size 4, we're going to calculate the min. And it's not all disjoint groups of size 4 like it would be in a segment tree. So in a segment tree, you would only have 2 nodes that are size 4, and it would be these 2 right here. For an RMQ, you're going to have n minus 4 nodes that each store a range of size 4. I guess it would be like n minus 4 plus 1. So n minus 3 ranges, each of size 4. So this first one would look at these first 4 nodes, or these first 4 elements, and it would find the minimum across all of them, so this would be 1. The second one would also be 1 as well. The next one would look at these 4, and the answer would be 2. And you can see how that would progress. And we do this for size 1, this is size 1, we do it for size 2, we do it for size 4. We're also going to store them in for all groups of size 8, etc. So we're going to do this for all powers of 2 in the entire array. So that'll work pretty well. And then we have all of these numbers. So one thing that I've kind of skipped over is for looking at groups of size 2, it's pretty easy. We can just look at this element and look at this element and take the minimum. But for groups of larger powers of 2, if we iterate through all of these powers of 2, we have order n of these large groups, and each group can be roughly order n in size. So just for building one of these layers, if we do it naively, it might be n squared, and we want to avoid that. So what we can do instead is for these larger groups, what we can do is each of these groups of size 4, we can look at this power of 2 and this power of 2. So we can imagine splitting it in half. Each of these will be a smaller power of 2, both of size 2 in this case. And we take the minimum of those, and that'll be the minimum for this, this range right here. So if we do that, then we can build each particular element in order 1 just by looking at 2 other things and taking their minimum. And we can build this whole thing in n log n. Why is it n log n? Well, there are n different positions here, and the height of this thing is log n, because there are log n different layers. So once we have this structure built, usually I'll call this an RMQ, this type of structure. Once we have this built, we can answer any query on the entire array. for any minimums. So that isn't obvious at first. It's pretty clear that like if your range is a size that's a power of 2, well then this corresponds right to this element right here. So we can just find this in our lookup table and answer right away. But what if this range that we're trying to look at isn't a power of 2? So maybe it's 3 long. So maybe we're looking at this range. Well, what we can always do is we can take this range and we can find the largest power of 2 less than its length. So it's 3 long, the largest power of 2 less than 3, or less than or equal to 3, would be 2. So then what we're going to do is we're going to take the first 2 elements here and the last 2 elements, and the union of these 2 ranges will be this green range here. The union of the 2 red ranges will be the green range. So what that means is we can look at whatever range corresponds to these first 2, take the min of that and whatever range corresponds to the last 2, and that'll give us the min for the whole green range. So by doing that, we can always look at exactly 2 elements, or up to 2 elements in our lookup table, and that can correspond to any range in the entire array, any consecutive range that we want. Let's do another example. So maybe we want to look at something that's 5 long. We can look at the first 4 of things and the last 4 things, and then whatever the min is, it's going to be in one of those 2 ranges. So when we take the min of those 2 ranges, then we'll get the answer. So this works very well for minimums, but we can also use this for other things that you might not expect. So let's look at what some of those things are. Obviously, if it works for minimums, then you can just replace all of your min calls with maxes. So you can also find the max of some range. In addition to finding the min or the max, you can do something that's very similar to min, like GCD. And GCD is basically you take the minimum of all powers. So all of the, like you write out your prime factorization, you have all of your exponents. If you take the min for each exponent of each base, that will be what the GCD is. So these are very similar, and you can use an RMQ for GCDs as well. Also for LCMs, because LCMs are similar to maxes. Instead of taking the min of each exponent, you take the max of each exponent. The final thing that I'd like to talk about that you can use RMQs for, which is actually super interesting, is for LCA. So this stands for lowest common ancestor. So let's say you've got some tree. Maybe this is your tree here. And what your goal here is you want to find, maybe you're given 2 nodes, so maybe you're given this node here and this node here. And you want to find what is the lowest node that's an ancestor of both of these nodes. So in this case, the answer would be this node here. And you want to find this node relatively quickly. So what you can do is you can do this thing called an Euler tour through the tree. And you can, like, imagine drawing this path. You can do this with just a DFS. It's pretty easy to code. It's just a pretty straightforward DFS. But you can do this, and then every time you reach some node, you can add it to some array. So the total length of that array will be the number of nodes plus the number of edges in the tree, because you hit each node once, plus once for each child edge that it has. So this node will be in the array 3 times. And then this node will be in the array 3 times as well. This node will be in the array just once, this once as well. You kind of get the pattern. So then what we can do is, if we want to find the lowest common ancestor between these 2 nodes, what we can do is we can look at the path from the first time that we see the first node all the way to the first time we see the second node, like this. And then along this path, what we want is we want the highest node on the path. So we can store the depth of each node in the tree. And what we want to find is what's the highest node, so what's the lowest depth, and which node does that correspond to. And we want to do this on some range of the array. So you can see if the green line represents the entire array, the yellow line is going to be some continuous range. And all we want to do is we want to find like some minimum node with some way of ordering nodes. And how we order nodes is just we order them by their depth. So we just want to find what's the minimum node on this array, ordered by depth. So we can do that to find LCA in order 1. And that might be a bit surprising because most of the time people find LCAs, they do it with binary lifting, and that has a log factor. So that uses log n time to find the LCA. but you can actually do it in order 1 using this. There's also this other algorithm named after 2 people whose names I forget that can give you LCA in order 1, but this is kind of a way to do it that's very easy to understand, in my opinion. All right, so those are some use cases for LCA, or for RMQs. One more thing I'd like to talk about before I talk about some optimizations you can do to the RMQ is kind of another problem that comes up a lot if you're familiar with it. So suppose you're given some array of integers, and what the problem is in this case is for every left endpoint, you want to see how far right can you go, so that, let's say we're considering this range. So we want to find the maximum size range we can do for every left endpoint, where every pair of numbers in this range are less than, or like are within k of each other. That's what our goal is. So maybe this pair is within k. Maybe if we look at some other pair, maybe this pair here is also within k. Maybe this pair here is within k, but this pair here isn't within k. So in that case, the range would be bad if these two are too far apart. But if every pair of numbers within this range is within k, then we're fine. So that might seem like a little tricky of a problem to solve initially. One thing that you might notice if you think about it for a while is that for a given range, the only thing that matters is what the smallest and the biggest element in that range are. Because the biggest difference between any pair of numbers is going to be the biggest number minus the smallest number. So if those two numbers are fine, then every other number will also be fine. Every other pair of numbers will be fine. So what this corresponds to is, in order to check some range, what you need to do is you need to find, all right, what's the minimum in this range, and also what's the maximum in this range. And if you have both the min and the max, then you can find the distance between the farthest pair of numbers. So what that lets you do is that lets you binary search on this RMQ. You're going to build 2 RMQs, one for the minimum and one for the maximum, so you can answer both the minimum and the maximum in order 1. And you can binary search for each left endpoint. How far right can you go so that the max minus the min is less than or equal to k. And that lets you solve this problem really quickly. So since you're binary searching on an RMQ, you can solve this in n times log n time. Since each of your queries take log n time, and you have to do n different queries, and then it also takes n log n time to build the RMQ. All right, awesome. So what if you used a segment tree for this instead? Well, you might be able to do some interesting stuff with like creatively walking down the segment tree, but that either requires thinking about it a lot more, or like doing something else interesting. But if you don't do that, if you just try and binary search on a segment tree, then you have this extra log factor. And if n is like roughly 10 to the 6 or something, then this will take approximately 4 seconds. So if you have like a 2-second time limit and n's 10 to the 6, this won't be a good solution for a segment tree. You'll have to find some other optimizations. But if you just use 2 RMQs, you should be able to get it correct fairly quickly. Awesome. All right, so the next thing I'd like to talk about with RMQs is a quick optimization we can do in order to make them be built a little bit faster. So I mentioned earlier, building an RMQ takes n log n time. And one concern we might have is that if we want to build a bunch of RMQs, maybe we want to build 1 RMQ for each bit, or maybe we want to build log n RMQs for some other reason. If we do that, then the total runtime is going to be n times log n times log n. And that's n log squared. So sometimes that might be okay, but maybe it's not okay. The other issue is if we need to keep all of these RMQs in memory at once, then our total memory usage is also going to be n log squared. And n log squared memory often is quite a bit of memory, and a lot of times that's not going to be okay. So we need to somehow fix it. Well, one thing we could do is maybe we could use a segment tree instead. And segment trees, we can build those in order n. And they also take order n memory. So segment trees in this case might be more helpful. The issue with segment trees is they add another log factor to our runtime. So if we need n log n segment trees, and we're doing a bunch of queries on them, then we might have really slow queries, and that might be an issue for the problem. So instead, what you can actually do is you can build RMQs in just linear time, also with linear space. How do you do that? Well, let's talk about it. So what we had earlier is we had a bunch of indices in our array, and we built an RMQ on these indices. So we would build some RMQ on this range. And if there were n elements here, then our runtime to our RMQ would be n times log n. Instead, what we're going to do now is, instead of considering a bunch of elements, what we're going to do is we're going to take this range and we're going to split it up into a bunch of chunks. And the size of each one of these chunks will be log n. So this is how wide each chunk is. In reality, we're not going to use log n, we're going to use 32, because there are 32 bits in an integer. But it's conceptually about log n, because we know n is not going to be bigger than 2 to the 32. So the size of each one of these chunks is log n. This means instead of there being n elements total, what we're going to do is we're going to build an RMQ where the number of elements, like each element, is going to be the min of this entire chunk. So we're going to have each of these elements, but the total number of elements in this like compressed array isn't going to be n. The total number of elements is going to be n divided by log n. And this is like noticeably smaller than n. It's like, well, I guess it's n over 32, so it's 1/32 the size of n, approximately. So when we do this, what the actual size of this RMQ is going to be is, instead of this being n, this is going to be n divided by 32. Really n divided by log n, we'll say. And now this, instead of this being log n, this is going to be times the log of n divided by log n. Well, this part here, this is slower than order n, or this is faster than order n, so we can just replace this by just n, so it's pretty much equal to log n. And if we have this, we'll notice that these two logs cancel. So our runtime now is really order n, just to build it. But, I hear you ask, that causes a pretty big problem, because now we can only answer queries that start or end at the end of these boundaries. So if we want to answer this query here, well, we can answer that, because that'll just be the min of like these 3 elements here, for instance. But if we want to answer some query that uses some of these elements here, like these ones, or maybe our query uses elements on both sides, maybe we need those elements and these elements, then we have an issue, because we don't have nodes for all of these elements, so we can't just look in our RMQ and figure this out very quickly. And that is a problem indeed. We have a very good solution to this that I'll talk about in a minute. But for now, what we can do is, we know the size of these blocks is at most log n. So we can naively iterate through each of these positions on both sides, and that'll make our runtime for answering a query log n. So the query is going to be log n. The build time, like we just discussed, will be order n. I guess I don't need parentheses here. And I don't need parentheses here, I guess. Let's just ignore the order part. So the build is linear time, and the memory is also linear. So this seems like a bit of improvement, because originally what our chart looked like was our query was order 1. This was n times log n. And this was also n times log n. So we've kind of like taken this log here and we've moved it into the query instead. So this seems like it might be helpful. The issue though is, if you think about this for a minute, you'll see this is really just completely useless. And the reason why is, well, what if we did a segment tree instead? If we did a segment tree, all of our queries would be log n. Our build time would be linear, because the segment tree has order n nodes, because each power of 2, you go down the segment tree, has twice as many nodes. So the total number of nodes you have is like n plus n over 2 plus n over 4, which is equal to 2n. And the memory for a segment tree, well, each node uses a constant amount of memory. So the memory for a segment tree would be linear as well. And this is exactly what we've managed to work ourselves up to with this RMQ. So this wouldn't really be useful. The only reason I'm showing it at all is because it makes for a really good stepping stone to how to turn this from log n to order 1 query. So this is ultimately what we're going for. And you can see this is better than a segment tree. And it's really helpful if you have this constraint on memory. Okay, so the only part we have left in order to do this really well is we need to be able to answer these small queries. So queries of length less than log n, we want to be able to answer all of those in order 1. And if we can somehow do that, then that will let us answer any query on the entire array in order 1 time. Because if the array is just smaller than log n total, well, we can answer those with a special method that we're about to talk about. But if it's bigger than log n and it crosses some of these blocks, then we can answer all the part of the array that crosses all of these blocks. We can answer that really quickly by looking at our compressed RMQ. And then we can answer all of these really quickly by looking at this special method here. So what is this special thing that I've been talking about? What does this actually look like? Well, there are 2 ways of doing it. One way uses a method of for Russians, but that's really complicated, and in practice, I don't think it would save any time. So instead, I'm going to talk about this way that uses some bit magic. You can use like the bits of an integer, and you can use that to store a bunch of information. So we're going to store n integers total, and we're going to have some array. So let's look at some example. Maybe the array is like 1, 2, 7, 4, 8, 9, 6, 7. And now we have like maybe some 8 here, or maybe we have some 10. And let's add one more element, just as a good example. So maybe we have a 6. So what we want to do, let's say we're considering this 10 here. This is going to be our right endpoint. So for every index in the array, we're going to say, if this is our right endpoint, when are there new minimums going to the left? And we want to store that for the next 32 elements. So for this 10, when are there new minimums? Well, there's a new minimum, I guess there's a new minimum at the 10. There's also a new minimum at the 7. There's a new minimum at the 6. The 9 isn't a new minimum because it's bigger than the 6. Same thing with the 8. But the 4 is a new minimum, the 2 is, and so is the 1. So all of these places that I've put 1s are new minimums, and then I'm going to put 0s in positions that aren't. And what this kind of represents is we now have this binary bit mask of all of the places where we have new minimums. So now, what if I give you some query, and the query looks like this, in this range? All you need to do to answer this query is you find, okay, the right endpoint is the 10, so we're going to look at this bit mask that I've drawn here, and we need to find the leftmost minimum that comes after this 8 here. So we want to find the leftmost one in this bit mask. What we can do is, since this is our range, we can AND this number with 0, 0, 0, 0, 1, 1, 1, 1, 1. If we AND it with this, then what we'll get will be 0, 0, 0, 0, 0, 0, 1, 1, 1. It doesn't necessarily end in a trail of 1s, but it might in this case. So now we just have to look at the highest 1 bit, or the leftmost 1 bit in this binary number, and that will tell us that the minimum is at this index here. The minimum is this 6. That's what we want to do. So, okay, a couple steps that I skipped over, I guess. How do we get this bit mask very quickly? Well, this thing here is just going to be a 1 with a bunch of zeros after. The number of zeros after is just going to be the length of this range. And then if we subtract 1 from this number, then we'll get this number. So we can get this, we can subtract 1 from it, and if you do the math in binary, then you'll get a bunch of 1s. In the same way that if this was a base 10 number and you subtract 1s, you get a bunch of 9s. So that's how you get this bit mask to AND it with. And then we just have to get this leftmost bit. So we can do that with getting the leftmost bit, and I'm pretty sure there are like built-in hardware methods for that in C++, and in Java there's highest 1-bit, lowest 1-bit, stuff like that. Okay, so now I hope I've convinced you that if we're somehow able to get these bit masks for every position in the array, then we can answer all of these queries of length less than 32, because there are 32 bits in an integer. So awesome. So let's say we can do that. So now the question is, how do we get these bit masks for every position in the array? It's a bit tricky. It's a little tricky because if we just did it naively, if we looked at each element and we walked 32 steps over, then our total runtime would be n log n. Our total memory would only be linear because we're only using order n integers. But our total runtime would be n log n because we have to start at each integer and walk left a bunch of spaces, and then we start at this other integer and walk left a bunch of spaces. So that isn't super great, and that would not really improve to the degree we want it to, because we'd still be worse than segment trees in some instances in building. So let's look at it slightly differently. What we're going to do is we're going to notice, let's say we're looking at this number here, and we want to find the answer for if our right endpoint is this 6 instead. So we're going to try and find the answer for this 6. For the 6 is going to be a minimum. This 6 won't be a minimum because it ties with this 6. The next minimum will be this 4, and then after that the 2, and then after that the 1. In this case, we won't actually store the 1 because like this isn't quite 32 bits. This is what, 9 bits. So I'm only storing 9 bits here, but you can imagine this were 32 bits, so we would drop this leftmost bit here. So that's why I'm going to ignore the 1. So we start with this bit mask, this top bit mask, and we're trying to get to this bottom bit mask by doing some creative stuff. But we want to do roughly a constant time number of operations. That's what our goal is here. So what we're going to do in order to accomplish that is we're going to keep a stack of all of the minimums. So I'm going to draw this stack right here. And what the stack will have on it is we'll have the 1, the 2, the 4, 6, 7, and 10 for when we were here. Then when we switch to the 6, we can remove the new minimum. So we can remove this 10, we can remove the 7, we can remove the 6, because all of them are bigger or equal to the 6 that we have here. So we can pop things off the stack, and each time we pop something off the stack, we can replace its 1 bit with a 0 bit. So we can delete that, replace it with a 0, replace this with a 0, and replace this with a 0. Then after we do that, we can add 6 to the stack and put a 1 bit here. In order to do that, we have to shift everything over by 1. So really what we'll do is we'll shift everything over by 1. So we move everything over. When we do that, this is the biggest bit of the integer, so this will fall off the end. And then after we've shifted everything over, we can take this 0 and replace it with a 1. So now we have exactly what we were trying to figure out, and we've also maintained this stack. I guess a little bit of bookkeeping that should be done in order to show that this is actually linear is, well, it might seem confusing because on a given step, we might pop log n different, we might pop 32 different things off of the stack. And if you pop 32 different things off the stack at every step, then your runtime is going to be n log n again. That's true, but you can't pop 32 things off the stack at every step because you only add each thing to the stack once. So the total number of stack operations you do is order n, which means the total runtime of anything relating to the stack is going to be order n. And then all the other operations we do here are just order 1 bit operations, and we do a constant number of them per right endpoint. So that's, I guess, what we're looking for, just a linear build time. So now that leaves us having achieved a build time of order n with order n memory, and we can answer all of our queries in order 1. So this is exactly what we were looking for, and it's quite fast. There's, I guess, one caveat that I should mention here. If you're doing like a binary search on an RMQ, lots of acronyms here. If you're doing a binary search on an RMQ, that means you're going to do n log n queries total. And if you're doing n log n queries, really you just want your queries to be as fast as possible. It doesn't really matter what your build time is, Because if your build time is linear, your build time is n log n, your runtime is still going to be n log n anyway. And when we do these second type of order 1 queries, although they're still order 1, they're about 30 or 40% slower from my implementation of it. So in this case, if you're doing like n log n queries on the RMQ, or you're doing more than order n queries on the RMQ, it might not actually be helpful to build it in order 1, or build it in order n. Because building it in order n, it speeds up your build phase, but if you're doing a bunch of queries anyway, really what matters is the query phase, and you can get a little bit faster if you do just the normal RMQ that we talked about in the beginning. The other thing to keep in mind is in code forces, this is really helpful because a lot of times if you have complex solutions, you might run into memory limit issues. But in things like ICPC or maybe USACO, where you have to type out all of your code in contest, during the contest, you might not want to use this method if you don't need it, because it's like about twice as much code. So you're going to spend more time typing, and if it's not actually going to be the difference between getting the problem correct and getting it time limit exceeded or memory limit exceeded, then you're kind of just wasting your time. So it's definitely helpful to at least have the simpler version of the RMQ, because although it looks like it would be completely unnecessary because you can do just a strictly better version with the more complex version, it's more code and the queries are a constant factor slower, so it might be not super helpful in some cases. So that's it for RMQs. Hopefully you've learned a little bit about it, and hopefully even if you knew all of this stuff already, hopefully the linear speedup might be something that's helpful, as well as the LCA query that you can do with an RMQ. See you probably in the @coder grand tomorrow morning, or if not, at least for the Div 2 on Sunday.